In this lesson, we're going to be looking at how to find the area that's bounded by curves. First thing, let's go back and kind of get an idea of what we're going to be looking at. We have two functions here. We've got f of x, which we've shown as this function. And then you've got g of x, which is shown here. And what I want to do is I want to find the area that's between the two of those. So what we've got is we look at when we found areas using Riemann sums, that we would draw a rectangle and then find the area of each one of those individual rectangles, add those up, and that would give us the total area. Well, if you'll notice, we're kind of doing the same thing here. We're going to be drawing rectangles, and we're going to find the area of each one of those rectangles, and we're going to add that up, but we're going to do it now in integral form since our Riemann sums were just approximations. So if I look at this particular problem, let's go ahead and try to set up a generic formula for how to find the area here. So first of all, if I look at just finding the area of one rectangle, we would want to do the length times width. So in this case, now remember, we're not going to know how wide these rectangles are because if you go back to our idea of our Riemann sum, we would want to do an infinite number of these rectangles. But I do know this, for this particular rectangle or set of rectangles, the width of my rectangle is going to be some delta x. So that's going to be our dx. The length of our rectangle is going to be the height, which if you notice is going to be bounded by our two curves. So in this case, we would want to take whatever the height is on the top curve minus the height on the bottom curve. So we're going to take our top minus our bottom. That's going to be our length, and multiply that by our width, which is dx. Now, once I do one of those rectangles, what I want to do is I would want to do an infinite number of those. So to do that, we're going to do an integral, and then we're going to go ahead and label our top function as f of x minus our bottom function, which is g of x, so that's going to be our length, times our width, and our rectangles are dx wide, and then we're going to integrate from a to b. Now we want to take a minute and just look at two different things that can happen with our equations. If you look at the first one, we've got y equals x squared plus 1, and then y equals x plus 3. So we've sketched those graphs, and what we're doing is we're trying to find this enclosed area. So what you might want to do is just draw like a representative rectangle, just one rectangle, and it would look something like that. Then if I want to find the area of that, I would want to do the integral. Since the width of my rectangles would be a change in x, that's going to be dx. We'd integrate from point A to point B, which in this case, our area starts at -1, and it ends at, looks like 2. And then I would do my top function, because this is going to be my length of my rectangles now, and that would be x plus 3, minus my bottom function, which would be x squared plus 1. And then we'd integrate dx. The other thing that can happen is our rectangles or our shapes could be in like an x equals equation. In this case, they've actually went ahead and solved them for y equals. But what's going to happen here is we have to be very careful about drawing our rectangles like this. If we draw them as a dx rectangle, notice that what's going to happen is that you have different top and bottom depending on where that rectangle is drawn. So in that example, what you'd want to do is rather than draw it as dx rectangles, we'd actually draw them as dy rectangles, and we're going to put them on their side this time. So I'd want to draw them like that. See if we can do a little better job of that one. So I might want to draw them like this. When you do dy rectangles, your width of your rectangles now changes to dy, And the height of your rectangles are not going to be top minus bottom. They're going to be a right minus left. So then what I would have is I would have an integral, and I'll just go ahead and give a generic form here for this one, of a minus, or from a to b. And then I would take my width, which is dy, times my length, which in this case would be our right minus our left. And again, because this is a dy problem, you're going to want to make sure you've got your equation solved for x equals. So if I go back up here, I could square both sides and get y squared is 2x plus 6, subtract 6 and divide by 2. That's what I'd use for my parabola that's on its side. And then solve the second equation for x equals, and we get x equals y plus 1. So if I did set up now the formula for this particular one, we'd go, the right would be our line, which was y plus 1, minus the left, which was our parabola, y minus 6 over 2, dy. And then my limits of integration, because it's a dy, I need to get the points of intersection here, and I want to use the y values. Now, I'm not going to solve this algebraically for right now. I'm just going to assume from the picture that these intersect at y equals negative 2, and it looks like they intersect right there at the top at y equals 4. I could actually solve that algebraically and make sure that did happen. Okay, let's move on and do a couple more examples. All right, let's say we want to find the area bounded by y equals x squared plus 3, y equals 0, which would be the x-axis, x equals 0, which is the y-axis, and then x equals 3. Okay, so we're looking for this area right in here. I'm just going to set up the integrals. I've gone ahead and graphed my functions. So I would do this as a dx, because if I do top minus bottom, the top is always going to be the parabola, the bottom is always going to be the x-axis. So I would do the integral from 0 to 3, and then the length of my rectangles would be top minus bottom, x squared plus 3, minus the bottom is 0 because it's the axis. You don't really have to put that. Then it's a dx problem. All right. Here's an example of one that's going to be a dy. This time we're going to take x equals y squared and x equals 2. So I've already sketched the graphs, and I'm going to find the area here. So I could set up my integral. Now, I want to draw my rectangles as a dy problem. I can actually do them as a dx. But if I do that, I'm going to have to be able to solve this equation as for y equals. And if I do, I'm going to get two different functions. I'm going to get, if I have x squared equals, or x equals y squared, then when I solve for y, I get y equals plus or minus the square root of x. So the top would be square root of x, the bottom would be negative square root of x. So I could do it as a dx, and I'll set that up here in a minute. But it's a little easier to do as a dy. So I'm going to set this up to go from, and I have a couple options here. I can either do from those 2 points of intersection, which are not going to be very nice, because if I set x equals 2 and x equals y squared to each other, I get 2 equals y squared, so y is plus or minus the square root of 2. That's my points of intersection. So I could do negative 2, or negative square root of 2, to positive square root of 2. I want to do it as a dy. And then if I do it as a dy, it's going to be right minus left. Right would be the line 2, minus left would be the parabola, y squared. Okay. As I said, I could do this as a dx. Okay. If I do it as a dx, I would want to draw my rectangles kind of like that. So that would be my dx rectangles. And then it would be the integral from 0 to 2. And now my height, my width is a dx, but my height's going to be top minus bottom. So that's square root of x minus negative square root of x. And then I could get that to be 2 square root of x. So either one of those would work. We're going to look at one last problem. I'm going to take some time to actually sketch the graph of this one. You have y equals 4x minus x squared and y equals 2x. So we'll start by plotting some points for 4x minus x squared. If we let x be 0, we're going to get 0. If we let x be 1, we're going to get 3. If we let x be 2, we're going to get 4. If we let x be 3, we're going to get 3 again. And if we let x be 4, we get 0. So then if I connect the points there, you're going to see that you have an upside down parabola, which we should have known from our equation. Then we're going to graph y equals 2x. So we'll have 0, 0. Then we're going to have 1, 2, and 2, 4. So if I connect those, I have that. And so what we're looking for is this part right in here between those two curves. So I'll kind of redraw it and enlarge it. So that's what we're looking for. So I'm going to draw my rectangles as dx rectangles. So I'll set up an integral from 0, and they intersected here at the point 2, 4. So I go 0 to 2. Since I'm doing as a dx, I'm going to do top minus bottom. The top is going to be my parabola, 4x minus x squared, minus the bottom, which was my line 2x, and then I'll have a dx there. We'll erase the parentheses out we don't need. And now I could do some simplifying if I actually had to integrate this, and simplify down to just 2x minus x squared, and then integrate that and substitute in my numbers.